this unit 2, we're going to look at the principles of computer graphics. By way of introduction, we notice that one of the key activities that we do in product design is, once the geometric model is conceptualized, that is, if we have a concept that we've sketched, we need to develop the model from that concept. Now, once we develop the model, we can then augment it with some engineering information, such as maybe material and manufacturing information. Now, having the ability to display these models requires the use of the computer, obviously. And this is an area in computing where one will utilize both utilize computers to both to generate visual images and also integrate or alter the spatial information from the real world. That is, of course, once we have to display these components in the drawing, that is in CAD, computer-aided design, we require the use of computer graphics technology. So in computer graphics technology, we're going to use the computers to do two things, both to generate the visual images and also to integrate or maybe alter the visual or spatial information from the real world. In this unit, what we're going to do is we're going to look at various geometric modeling approaches, such as what we call the wireframe modeling, surface and solid modeling. We will explain these things further, but we will introduce these concepts or approaches to modeling. Then we look at the basic computational geometric methods for defining simple entities, such as if you have curves, you have surfaces, you have solids, and we cover all these. So, by way of learning objectives, at the end of this unit, we expect to have covered the following. That is, we should be able to define the various geometric modeling representations. We should be able to define the various geometric modeling representations. We should be able to listen the types of geometric solid modeling techniques, explain the various solid modeling techniques as well, determine the validity of a solid. That is, if we have a representation on the screen, we should be able to determine whether or not this representation is a valid solid. We will come to some concepts to understand that. Now, we should be able to also explain various CAD data exchange standards as well. Now, the unit content. What we're going to cover in this unit is in two sessions. Now, session 1 of this unit 2, we'll look at computers and geometry. And then session 2, we'll be looking at three-dimensional modeling, where we'll look at these types of modeling techniques: wireframe, surface modeling, solid modeling. And then we'll look at the Euler-Poincare equation, the equation that will help us to determine whether or not a representation is a valid solid. Now, we begin this section or this unit by looking at computers and geometry. Now, when we talk about geometry, we've all done a little bit of maths. Geometry is simply a branch of maths which is concerned with description of shape, size, and relative positions of figures. and properties of space. Now, that is geometry we know from mathematics. When it comes to computers, on the other hand, computers don't know anything like figures or lines or whatever, but computers deal with numbers. Now, what it means is that if you want to represent a shape on the computer, it requires a translation of these shapes, these geometrical shapes, into the numbers that the computer understands. Now, that method that is used to convert the geometry into numbers is known as the coordinate geometry. Now, it's made possible to describe the location of a drawing, such as the center of a sphere, where we can describe it by point coordinates x, y, and then z, Cartesian values. So, this is what the computer understands, numbers. So, the method that is involved in the use of these numbers to actually convert a geometry is called the coordinate geometry. Now, let's look at some basic geometric entities that constitute an object. When you take a manual drawing, or when you create a manual drawing, what you basically see is an assembly of points, lines, arcs, and circles. So if you look at this figure we have before us, we could see that this arc here is made up of a circle or arc. Of course, this edge is a line, and then there's a point here which can be or a vertex here which is a point. So this knob, which is a door knob that we have in view, is basically made up of points, lines, arcs, and circles. So what it means is that if you take, that is one example. Let's take another example before we come and state our observations. If you look at the second figure here as a section of a wing of the aircraft. Now this aircraft wing has a surface. Now the edge is defined by a line. Now there is a tip of it, which is a point or a vertex as we describe it. Then the whole wing can be qualified as a solid. So from this, if we consider this section, we notice that generally there are essentially four geometric components or entities that constitute an object, and they are the points or vertices, lines and curves, surfaces, and then solids. Now, when we take each of these geometric entities, we can try to define them, attempt to define it. When we say a point, what is a point or a vertex? We basically describe a point as, or a vertex, as a zero-dimensional entity. A point has no dimension. And what a point does is it defines a location in a three-dimensional space. So you notice in a Cartesian coordinate system, a point can be described as a triplet of numbers, x, y, and z. Okay. Now, when we come to a line is basically, or a line or curve, is a one-dimensional entity. So typically we have a point. When we have a point in space, we can just have a point, and then that point, if it's on this two-dimensional plane, we can just use an x-y coordinate to define the point. But in a three-dimensional space, you have x, y, z. Now, if you have a line can simply be described as a one-dimensional entity. And a line is formed from a locus of moving points. A locus of moving points. And a line could have an infinite length. So when we say a line, it's basically a locus of moving points and it's up to infinity. So, typically, if you want to describe a line which has a definite length, then it is called a line segment. So we use the term a line segment to define a line and two endpoints. That is a line that we can define by two endpoints. So a segment is defined by a line and two endpoints. So that line should have a start point and then an endpoint defined by a coordinate system. So that becomes a line segment. So a line could definitely be defined in several ways. You can have a line or curve. So the line, depending on the type, it could be a straight line, it could be a circular arc, an ellipse, a helix, etc. They are all lines in particular shapes or types. So that is the definition of a line. Now when we come to, so that is a line. Now when we come to surfaces, when we say a surface like this plain paper surface, this plain paper is, the surface of this plain paper is the typical example. Now, a surface, or normally what we call a face, we can use the screen that you see and view as a surface as well. It's basically a two-dimensional entity or two-dimensional entity that can be drawn in a plane. So once I can draw a two-dimensional entity like that in a plane, then I have a surface. Now this is a plane which is not deformed, but we can have a deformed plane like the section of the wing of the aircraft. That surface is a deformed plane like this surface over here. So there is a plane surface, but it's deformed. So in this deformed plane, it's still a plane. So the plane can be just a plane surface, straight, or deformed plane. Now it can be defined as, of course, surface, a plane is a surface. If you have a cylindrical surface, it's also a surface. You have a sphere, the surface is also, you have a cone, it has a surface, and others. Now, planes, cylinders, and cones, this family, are known as natural quadratic surfaces. So this word is actually quadratic, natural quadratic surfaces. Now, it is because these surfaces can be defined by a second order equation. So if you take a circle, here, then you have a typical circle, the second order equation, x squared plus y squared is equal to r squared, which is the radius. So this is a natural quadratic surface. Now, the fourth geometric entity is the solid. Now, when we say a solid is a three-dimensional entity with a definite shape, volume, and a mass. So this marker is a solid because it is a three-dimensional entity. It has a definite shape, it has a volume, and of course it has a mass. So anything that has a definite shape, volume, and mass is a solid. Right. So once we have seen these geometric entities being points, lines, and then surfaces and solids, these geometric entities undergo what we normally call transformations. So let's try to understand transformations. Now, when it comes to transformations, in geometry, they provide a means by which the orientation, position, or size, or shape of an image can be changed. Now, the changes come about by changing something, which is the coordinates of the image, to a new set of values. Then you say that you've done a transformation. Now, this new set of values depends on the type of transformation required. Now, examples of geometric transformation, as we know from our geometry, includes rotation, translation, scaling, and mirroring. So we're going to pick each of these examples and look at how the computer actually undergoes this transformation or utilizes the numbers to perform these transformations that we see on the screen when we are dealing with solids. Now, in computer graphics, the transformations are implemented as what we call matrix manipulations on the coordinates of the points. So we're going to understand the principle behind these transformations by the computer using the computer graphics technology. First, we look at scaling. Now, how do we scale a drawing? A drawing is made bigger or smaller by either increasing the distance between them, the points, that is the points that form the drawing. You increase the distance between the points of the drawing, then you make the drawing smaller or bigger. Now, can be done by simply multiplying the coordinates of the drawing by an enlargement or reduction factor called the scaling factor. Now, once you undergo this process of either enlarging or reducing a drawing, then you are doing scaling. Okay, so let's try to illustrate that. Let's take this, for instance, this point xy here. Now, the point xy as depicted, if we undergo some transformation of this point xy into a new point x prime y prime, so basically we have this point xy p xy. Now, if we transform this point to a new point, say p prime, which we have x prime y prime. So we undergo some transformation, and this is what we get for a new position p. Now, if we are scaling, then this new position of x prime y prime, these coordinates can be determined by using the scale factor that we use in transforming the point xy to multiply the coordinates x and y. So the new coordinate x prime will be equal to the scaling that could be in the x coordinate position times the x, which is the original point, and the y prime will also be the scaling along the y-axis times the y, so that we get a new positions x prime, y prime. Right. Now, in matrix notation, if you want to represent this transformation in a matrix notation, it is basically writing as follows. That is, you have x prime, y prime to be equal to the scaling matrix will be a 2 by 2 diagonal matrix of the scale x suffix x, which is showing the x coordinate or x direction, times xy, So if we do the matrix multiplication here, basically, if you review your matrix, it's going to be x times x plus 0 times y. And then this is 0 times x plus xy times y. So you notice the answer is just going to be sx times x, and then this is 0 times x is also 0, and so you have xy times y, which is simply the new coordinate value x prime, y prime. So it's basically what we wrote before, which we said x prime, y prime, x prime is equal to sx times that is s subscript x, and this is xy times y. So that is the transformation matrix that we generate, a 2 by 2 matrix, which is this, which becomes what we call the scaling matrix. Now, we can use this example below to illustrate that. Suppose we have a triangle ABC with this point coordinates 3, 5, 1, 2, 4, 0. And we transform this by scaling to the new coordinates ABC with these coordinates. Now, we can basically look at the scale factor in that matrix. And you notice that A, the new A coordinates is 6, 10. So you could see that the x was multiplied by 2, the y also by what? 2. So basically, the matrix, the scaling matrix was 2 in the x and then 2 in the y. So that scaling matrix, which is sx 0, 0, xy, is simply a 2, 0, 0, 2 matrix. And this 2, 0, 0, 2 matrix was used to work on each of the points. So the new A position, if we define by x prime, y prime, is simply this 2, 0, 0, 2 matrix by the xy, which is 3, 5. And that basically gives you 2 times 3 plus 0 times 5. And then this is 0 times 3 plus 2 times 5. And that, of course, will then give you 6 and then 10. So that gives you the new position of A. And you can apply this to A, B, and C, and you get that result as shown. So this is how the computer will do the representation. The computer doesn't understand these lines or curves. So it generates a 2 by 2 matrix for the scaling, pick each of the coordinates, and operates on that coordinate using this transformation, and then generates the points for you. And it will display it by just increasing the distance between the points. And you have your objects blow up or increase in size on the computer, and you say that, oh, it's being scaled. But inside the computer, these sort of computation that I've displayed here is what is going on. So the computer does not understand a curve or a line, but it understands numbers. So this is the transformation that we sought to describe or explain. Okay, so that is scaling. Now we can look at translation. Now moving on to translation. Translation basically means if you move a model or a drawing across the screen, you move it from one position to the other, without necessarily increasing or changing the shape, or without changing the shape. Let me be definite on that. Translation basically does not involve any change of shape. So if you look at these two objects on the screen, if this is a location, the previous location, and that is a new location here, you will notice that there has been a translation of the same size object to a new position. So, when it happens like this in translation, what you basically do is that you actually transform this by adding the coordinates values along the two axes. So if this has to move how many units, the initial point 1, 1 has to move to start at 5. So it has to do a translation from x equals 1 to x equals 5, which is 4 units all to the x coordinate. Now, if you look at the current y value is 4 from 1. So it has to transform from 1 to 4, and that is moving 3 units and then moving 4 down here. So it means that we have moved the drawing by adding 4 units to the coordinate values of x and 3 units to the coordinate values of y. That is basically the translation that happens. Now, in translation, from a mathematical representation, if you are translating an x, y coordinate to a new x prime, y prime coordinate, what you're basically doing is that you're taking the x and adding a transformation units along that axis, which will be a change which we call delta x, and then you have y plus delta y, which is also a change along the y axis. So, if you look at this expression and you want to generate a matrix from this, in a matrix notation, this will be written as x prime, y prime will be equal to, you have an xy plus delta x, delta y, which is an addition of a unit matrix like that. Okay. We can use this to do any example of translation. If we know the change along the x and the y, we can just put in an operate on the values, and we get that. So, when we come to the next transformation, which is the rotation, we notice that rotation is also another transformation, which is, if you, for instance, say that you want to rotate a point from one position to the new position, as you can see in view here, then if I have to do this simple sketch down here, an yx, let's say we have this point P defined by x, y. This will be our x and our y values of P. Now we rotate this point. This P is making an angle, let's say phi, the horizontal. Now we rotate this point to a new position that can be defined by P prime. It is an x prime, y prime position. Let's say this point. So this is a new chord. That is moving this point through an angle rotation of theta. We define a new position of x prime, a new position of y prime. So, if we want to write a transformation for the new position, for the coordinates, then we will notice that it is basically this chord. If we define this chord, which we can call R, it's the same chord R here. What it means is that this R, the chord R, has now moved from this through an angle, what? Theta. Now, if you want to write the x-coordinate value for this transformation, you can basically see that x prime is the horizontal side. So, if you remember your simple trigonometry relation, this is the adjacent. So, adjacent is going to be given by this r cos the angle that is sustained. The angle that is sustained this time is r cos the two angles combined, because this chord sustains the new angle of theta plus phi, or we can write it phi plus theta. And if we expand this from our trig knowledge or trigonometry knowledge, which is r x prime, which is r cos theta plus phi, going to be given by, from trig knowledge, is r cos theta cos phi plus r sine theta sine phi. Sorry, r cos theta minus. Okay, so if we look at this sketch, we notice that r cos theta is actually equal to x, which is this transformation, this point coordinate. Because if we trace down here, we can define this point as the point x. Then we can define, we trace horizontal. We can define this point as point y. Okay. Then of course this one, it will trace down vertically. We can call it the x prime. And then we can also trace this and call these y prime. Okay, so the x is actually r cos phi. The x is r cos phi. And then you notice that y is also r sine phi. So it means that we can write x prime as shown here. That is, we can write x prime as r cos phi is x. So we can write it as x cos theta minus y, which is r sine phi sine theta. In a similar way, if we take y prime, which is going to be r sine theta plus phi, we can expand this just as we expanded the trigonometry for the cos, which is going to be, this is going to be r sine theta cos phi plus r cos theta sine phi. And if we do the analysis, we are going to also get this value, which is x sine theta plus y cos theta, as you can see here. So you have x prime as s cos theta minus y sine theta. And then we have y prime as x sine theta plus y cos theta. So, if you want to represent this in a matrix notation, this equation can be represented as x prime, y prime in the matrix notation is, we can bring that transformation matrix with the rotation matrix cos theta minus sine theta, cos theta, and then operates it on x and then y. And we can generate the above equations to form the transformation. So we can consider a point as we have in this illustration, 40-20 rotated by theta 45 in the anti-clockwise direction. Now, if we want to generate a new coordinate position, we just have to put theta is equal to 45 to generate the matrix and put a point 40-20 to operate on it. And this will be our final result of the new point for the rotation. Okay. So far you notice that from rotation, translation, and scaling, we've been able to do a matrix manipulation of these transformations. That is, we have been able to show how the computer will interpret these transformations. Now, you notice that there are some differences in these transformations. The scaling was different, the translation was different, as well as the rotation. Now, in a computer, the computer only understands all these scaling, rotation, or whatever as transformation. So it requires the computer to create a coordinate system that will, in its sense, homogenize the whole transformations, which is being rotation, translation, and scaling. So the computer introduced what we call a homogeneous coordinate system. Now, we notice that each of the above transformations, as I've already said, performed, they are different. Okay, with the exception of the translation, we have matrix multiplication. But for convenience, all the transformation operations can be made into a matrix multiplication by introducing the concept of homogeneous coordinates, which is introduced by the computer. Now, in a homogeneous coordinate system, you have a scale factor which you introduce with a Cartesian coordinate. So, any points that you have, let's say a point x, y, z, can be represented as x prime, y prime, z prime, and then the homogeneous coordinate omega, where this omega is not equal to 0. It should not be a value which is 0, and it's actually a scale factor, such that this x prime, new x prime, is equivalent to this new x prime is actually equivalent to the omega times x. In other words, if you want the x should be seen as the x prime over omega, then the y prime over omega, the z prime over omega. Okay, now in this homogeneous system, if you use in a computer representation or in a computer graphics application, this omega is equal to 1. Therefore, if you put 1 here and you are doing a transformation, of course, it means if you transform this to this s prime, 1 is not going to add anything to this value. Okay, so because it is equal to 1, this is how, using the homogeneous coordinate system, the computer transforms these three transformations, which is scaling, translation, and rotation, into. So, in a computer representation, what it does is that if we take scaling, if we want to generate a new position after scaling, the computer introduced a 3x3 matrix. But in the 3x3 matrix, what you notice is that it has a scale, the 2x2 matrix there, and then it has 0, 0, 1, 0, 0. So it actually introduces this and then operates it on an x, y, and then the homogeneous coordinate, which is the omega, and in computer is 1. So this gives you the scaling matrix. The translation, on the other hand, if you want to do translation to a new position x prime, y prime, this is what you have. You have 1, 0, then you have beta x, 0, 1, 0, 0, 1, then you have your data y, and you have your x, y, and then 1. Then you have your translation. Now, in your rotation, it's basically having the cos theta, sin theta, and then you have your 0, 0, 1. So it is actually multiplying, it's actually operating a coordinate unit diagonal matrix, what you call a diagonal matrix of A's. 1, 1, 1, 3 by 3 diagonal matrix. And then operating with the transformation matrix. Okay, that is the transformation matrix depending on which transformation, which is cos theta by cos theta minus sin theta, and then we have sin theta and then cos theta. So it does this transformation on all the translation vectors or translation matrices, and it generates these new translation matrices. So this is what the computer does. And so for the computer, it uses these transformations to operate on every single point. If you want scaling, it picks every single point on the drawing and then perform this matrix manipulation and then generate a new point for each of the points. Do all this computation and finally display the model as a scaled part. If you are moving the model from a new position, to a new position, perform this matrix manipulation and then generate you the new position. If you are performing rotation, it also does this operation and generates the new position. Now, by way of self-assessment, this is what we're going to do. Basically, you should be able to write down the matrix rotation for theta is equal to 90. So you can generate that by taking the matrix transformation here, rotation, and then putting theta is equal to 90 and generating these matrices. And then you write down matrix for translation of that, and a matrix for scaling. Now, you can answer some of these questions here. Now, you have vertex of triangle, which is these points, and the triangle is first giving a rotation about a z and then scale twice the size. You will have to find the coordinates of the vertices of the triangle after this transformation. You can also look at this 5, which is a point which is translated 70 units in the x direction, 50 in the y, and is also giving a rotation 20 degrees about the z. And you have to find the transformation of the coordinates of the final position of the point. Okay, so these are self-assessment questions that you can try. Right. So we're moving on to another session. We've done with the computers and geometry. We've been looking at transformation. That is rotation, scaling, and then, of course, translation. So now we're looking at the next section, which is an introduction to what we call three-dimensional modeling. Now, in wireframe, that is the first type of modeling, three-dimensional modeling or visual representation. If you come to three-dimensional modeling, you can display a model in a particular representation, and that is we have what we call the wireframe, and then we have the solid model or the surface model. So in wireframe, when we turn a drawing, a 3D object in a wireframe representation, what you basically see is you have the vertices connected using straight lines and curves. So this is a typical wireframe model of a connecting rod. You could just see the edges and the lines connecting the edges. Now, these terms come from designers using metal wire to represent the 3D shape of a solid object. So, to create a solid object, they will just actually use a bunch of metal wires and try to curl them into the shape required, and then they make it as a 3D shape. So they will be basically using the edges to do the representation, and that is what we call the wireframe. Now, a true wireframe model is basically a combination of a 2D elements in a two-dimensional space. So if you look at wireframe, the rendering is very fast. When we say rendering, what we mean is if you are displaying it in the computer and then you are trying to rotate it or show the views, they are very fast to calculate. You see, for every transformation you do on the computer, there is a computation going on. So when we say that it's fast to calculate, then what we mean is that the computer does a computation and is able to display it quite quickly. Now, they are often used in cases where you have high screen frame rate needed. Sometimes you have drawings that you will need to, you have a situation where the drawings are so huge that the rendering could take time. So once you turn the representation into wireframe, then it's fast to calculate and display the model. Now, this type of modeling can also be time consuming. The reason being that the wireframe model must be independently drawn in position. That is, each object that makes up this model. And because of that, it could be a time consuming type of modeling if you are just doing wireframe representation. Now, if you look at a wireframe, you basically have two tables that could help you to generate a wireframe model. One is the vertex table and then the edge table. Now, each entry of the vertex table records a vertex and its coordinate values. So, of course, a vertex will point here and then the coordinate values of that point. and then it uses to generate what we call a vertex table. Now for the edge table, it has two components, given the two incident vertices of that edge. So you have to have a start vertex and an end vertex. So a wireframe model actually does not have any phase information, as we know, because it's only looking at edges. So let's use this example of a cube to actually display what we mean by a vertex table and an edge table for a wireframe model. Now, if you look at a cube here, it is defined by 8 vertices. Now, these 8 vertices, which we can actually number them as number 1 here, and we can move maybe 2, 3, 4, and we can move on to 5, 6, 7, and then 8. Perhaps my numbering wasn't accurate, so we could just do it this way. Because I started here. What we can do is just come back. So this is 5, and then 6, 7 here, and then 8, just to make it an order. So these are the vertices. Now it has 12 edges. The first one between 1 and 2, 2, 3, 3, 4, and all that. We can count them 12 edges. Now, if we position the origin at the centroid means the center of these blocks, such that if we move out of these blocks, so I can just relabel them here, 1, 2, 3, then we have 4, 5, 6, 7, and then 8. So if we put these at the centroid, what we mean is the geometric center, so that if we move from the center of the box to any of the faces here, any of the edges here, just straight through the surface, then we cover 1 unit. Then we can define the coordinates values. If you take point 1, to actually get to point 1, we have to move 1 unit along the x, go 1 unit along the y, and go 1 unit along the z. So we go positive x in this direction, we go positive x in this direction, then we go to positive y in this direction, and then we come to positive z. So we have 1, 1, 1. If we want to go to 2, we have to go positive x, and then go to negative y, and then go to positive z. So you have 1 minus 1, 1. We can use that to trace all the coordinate points, the vertices 1 to 8. Then that is what we call the vertex table. And then the edge table generates, if you take this edge, it has to have, this is the first edge, it has a start edge 1 and an end vertex. It has a start vertex 1 and end vertex 2. Edge 2, of course, will be between 2 and 3. Edge 3 will be between 3 and 4. And that is how all the 12 edges are also populated. So this is a typical edge table and then a vertex table. So the vertex table and edge table for a wireframe representation. So every wireframe that you create potentially has these type of tables. Okay. We move on to also look at some features of the wireframe. Now, wireframe also uses what we call simple data structures, but wireframe can be ambiguous. The data structure that we're talking about is simply the vertex table and an edge table. Once you can generate this, you can create the model. But it is ambiguous. The reason why we say wireframe is ambiguous is that if you look at this image I have in view, if you are doing a representation in wireframe, it is very difficult to represent this point that I'm showing on the drawing because there are some interference in this view. You could see some interference in this view that you could see here. So you struggle to know whether this point lies on this edge or it lies on the vertical edge. So we say that the data structure could be ambiguous. So let's quickly look at the advantages of wireframe modeling or representation. One good advantage is that it's able to display 3D parts very efficiently. Now, when you save your drawing in wireframe, the file size is small, so you have small storage requirement, and then you can actually access it quite quickly. Now, wireframe can also be used to generate CNC toolpath. That is, when you have a CNC machine, you can use a wireframe representation to generate the path that the tool will have to travel to do the material removal for it to create the part. Now, the disadvantage for wireframe is there may be ambiguities in the interpretation of the data, as I have shown here. That the data, if you see the data there and there is a point here, it's difficult to know whether the point lies on this horizontal line or on this vertical. So that is about wireframe. Now we come to surface modeling. As the name implies, a surface model defines not only the edges of the 3D object but also its surface. So if I could get a typical surface model to show you, if you look at this solid cube here, how we are able to see the cube is that we are able to look at the surface represented by some colored area to actually give us an impression of the cube. So the modeling that is shown here is actually called surface model because you can see the surface which is defined. So just going back to define surface model is that it does not only define the edges of a 3D but also the surface. So when wireframe is used to represent the face, only the boundary of the face can be precisely represented, not the actual geometric property of the face itself. That can only be done in this surface modeling. So that is where wireframe has its limitation. It can only show the boundaries, but it cannot show the actual properties of the face of the object. Okay, now under surface modeling, we can look at a number of technologies or a number of entities here. That is, we are what we call surface entities. Similar to wireframe entities, existing CAD/CAM systems also give the designer both what we call analytic and synthetic surface entities. Now, the analytic surfaces are basically surfaces that can be described by surface equations. And we have the first one called a plane surface. When we say a surface is called a plane surface, it's basically the simplest surface that you can generate, which require 3 non-coincident points to define an infinite plane. So if I want to create a plane surface, I only need 3 points, which are not coincident, non-coincident, and I can join them and I've defined a surface. That is what it means. Now, that is a plane surface. Then we have what we call a ruled surface. Now, a ruled surface in geometry, when we say a surface is a ruled surface, then it means that through every point on the surface, if we can find a straight line that lies on the surface, then we can call it a ruled surface. Now, if you look at planes or cylinders or cones, these are typical or specialized ruled surfaces. In terms of construction, you see the ruled surface can be defined by an interpolation between 2 straight lines to a determined trajectory. Like if you take the cylinder is just, if you take the shape of this paper, and I have a point here, and I can draw a line across. Let's say this line is complete here. Now, if I take this paper and I curl it, and I form a cylindrical shape. Now, this line, if I pick a point there, I can draw a line to this point. And that means that this is a ruled surface, because through every point there can be found a straight line that lies on the surface. So that is a typical example of a ruled surface. So a cylindrical surface, conical surface, they are specialized ruled surfaces. Then we have a typical surface which we call surface of revolution. And I'm showing you this bottle on the screen. This is a typical surface of revolution. If I take this bottle, I can generate the surface of this bottle by simply taking a cross section, which will be defined by a planar curve. So I can take a section, I cut through this bottle, and I can see the curve that was used in generating this bottle. If I have this curve swept through or revolve 360, I can generate this bottle, and that is called the surface of revolution. Okay. Now, when it comes to surface modeling or surface modeling, some advantages are as follows. If you have a surface model, you can display the profile of the parts quite efficiently. It has small storage requirements. However, this is not as small compared with wireframe. Wireframe has a smaller storage requirement than surface model. Now, it can also be used to generate a CNC toolpath just as a wireframe. And the good news about that is it eliminates the ambiguity and non-uniqueness present in the wireframe model by hiding lines that are not seen. So the lines that are not seen are hidden, and then the surface is displayed, so you can really see it and there is no ambiguities. Now, it's also able to render the model for better visualization and presentation. The objects appear more realistic in a surface model. You can see it, and then you can feel that it is a real object. Now, another advantage is that it provides the surface geometry for CNC machining, so it can give you a profile of the surface for CNC machining. Now, it also provides the geometry needed for mold and die design as well, if you're doing die casting. Now, it can also be used to design and analyze complex preformed surfaces. For instance, if you take the hull of the ship or the airplane fuselage and all that, you can create them using surface models or car bodies. You can create them using surface models. Okay. So, surface properties such as roughness, surface roughness, color, and reflectivity can actually be assigned and demonstrated in the surface model. Now, the disadvantages of the surface modeling is that one, it gives you no information about the volume of the object. Now, that is the disadvantage. When you have a surface model, it is not able to interpret a side which is facing the outside from that which is facing the material, or what we call the inside. Once you have the surface representation, if you go into the system information, you are not able to distinguish between this surface and the other surface facing a particular direction. That is the little disadvantage of the surface model. Okay. Then we come to the third one. So we've done the wireframe surface model. That is two geometric modeling technique. The third technique is the solid modeling technique. Now, solid models gives you, or the solid model representation gives you a complete, unambiguous definition of the object. That is describing not only the shape of the boundaries, but also the object's interior and exterior regions. So we say that for any point in space, it is possible to determine whether the point lies on the inside or on the outside or on the boundary of a solid. Now, the solid modeling also allows you to represent more complicated shapes than surface modeling. So with solid models, you can actually compute the mass properties such as volume, moments of inertia, and also you can apply finite element analysis to calculate the stress and strain for the solid models. Now, when it comes to the solid modeling construction techniques, we have a number of techniques that you can use to create solid models. Now, the first is to look at what we call the PPI, pure primitive instancing. To create a solid model, one of the techniques is called PPI, which is pure primitive instancing. Now, to explain this, is basically recalling already stored descriptions of primitive solids. Now, basically, there are 5 primitive solids that we have. Now, when we say primitive solids, they are assumed to be solids that have their natural existence. Of course, you can then say that, well, created by God. You cannot break them down into other shapes which can be clearly defined. So, these are the primitive solids. First is the cube, the sphere, the cylinder, the cone, and this is actually normally called a torus. The torus or tori, or in some cases is simply called the donut shape. So this is tori, simply called the donut shape or torus. Now these are the 5 primitive solids, and you can use any of these combinations to create a shape of an object. Once you use any of these combinations to create the shape in the solid model, then we say that you are using PPI, pure primitive instancing technique. Okay. Now the second type of solid modeling construction technique is called the constructive solid geometry, which is the CSG. One of the most popular technique, CSG. Now in CSG, it basically uses Boolean combinations of super primitives to build a part. So CSG will deploy these primitives, some of these primitives, and do a Boolean operation, that is, do a union, subtraction, or intersection to create the shape. Once it involves these Boolean operations to create you the part, then we say you are doing a CSG, constructive solid geometry. We explain this further later on. And then we have what we call the boundary representation. Boundary representation basically consists of entering all the bounding edges for all the surfaces. So you can basically use your coordinate points and you enter and you connect them and create the boundaries of the surfaces and generate the drawing. We say that you're doing boundary representation. And then, of course, we have sweeping. Sweeping is basically something like creating a revolve or a translated shape. That is, you can actually sweep a channel. You can create a cross section and sweep a channel and form the shape, or you can simply do this revolve that we saw over here and create the shape. And that is a sweep, which is another construction technique. And then these two construction techniques, these last two fairly advanced ones, are one, the spatial occupancy enumeration, SOE, basically subdivides 3D space into volumes and classify them as either partially full or partially empty solid. Now, to explain this one, sometimes there are some very complex shapes that you want to model. Now, these shapes are not clearly defined by some standard geometries. So what you do is that you get the whole three-dimensional space and then you divide them into volumes. Now, once you divide it into volumes, then based on the complexity of the shape, you try to generate that complexity from the volumes. In some portions of the volumes that you have described, the shape will occupy the whole volume, so that place will be full, but in some volumes that you have generated, that shape will partially be occupying there. So you will have to distinguish between the volumes that are partially full, are full and partially full, so that in the end you will then eventually generate that complex shape from the SOE, which is spatial occupancy enumeration. And then when it comes to cell decomposition, the cell decomposition is similar to the SOE, but in the cell decomposition, you start with the object, not a 3D space. That is, in cell decomposition, sometimes you start by approximating the object and then you start chipping away. Cell decomposition, basically, if you want to explain, looks like how it's like sculpturing. In sculpturing, they take a solid mass of clay and they try to sculpt away the parts that are not needed to be able to then create the shape. So you start with an object and then you try to take away some portions to be able to get the shape required. So that is cell decomposition. Now, of the above list that we have looked at, the two most commonly used techniques are the constructive solid geometry, which is CSG, and then the BREP, boundary representation. So we have to take note of these points. Two most commonly used constructive solid geometry and then boundary representation technique. Right. Now, when it comes to constructive solid geometry, we are saying that it uses simple primitives such as boxes, spheres, cylinders, and tori to create more complicated shapes. Now, it uses the three Boolean operations: union, subtract, intersect. So, for instance, if you have a cylinder and a cuboid here, and you model them together, and you apply any of these Boolean operations. Let's say if you apply union, you are going to get a cylinder and a cube united this way. If you apply subtraction, that you subtract the cylinder from the solid, then this is the shape that you're going to get. Now, if you apply intersection, intersection is going to leave only the common features or the common parts that they share, and that is this, and then of course the curved shape. Okay, so the intersection will basically leave this that I'm trying to generate. Okay, so it will basically leave something like that, because everything will be cut out, and that is what the intersection will leave, as shown down here. So that's the common part of both the cylinder and the cube. Now, in constructive solid geometry, when you take Boolean operations, you can clearly see, if we look at these Boolean operations, they are intuitive to us. As users, we can clearly see that if you do union, you do intersection, you know the result. And it's very easy to understand. It gives us a rapid manipulation of large amount of data. We can actually do a lot of these techniques to actually generate very complex shapes, depending on what we take away and what we add. Now, because of this, even many non-solid constructive solid geometry systems also use Boolean operations. So it's not only in constructive solid geometry that they do use the Boolean operations, being union, subtraction, intersection. It is a very powerful modeling technique. Now, in constructive solid geometry, what you will see is that this geometry has a data structure. Now, the data structure that we have in constructive solid geometry does not define the model shape, but rather it implies the geometric shape through the procedure description. So, what you basically see is that if you construct an object defined by two set of edges and faces by an instruction like, let's say, union of primitive 1 with primitive 2. So if you have an object formed by two primitives, you just go into the data structure, and what you see is formed by a union, addition, union primitive 1, primitive 2. This is what you will see inside the stored data. This procedural data is stored in the structure in a form called what we call the constructive solid geometry tree, CSG tree. Now, it stores a very simple and it stores compact data, which is very easy to manage. So, if you take this as a typical constructive solid geometry tree, it has a history of applying the Boolean operations on the primitive. So it stores in what we normally call the binary tree format. Now, if we have this image or this drawing model, and this model is eventually generated from this Boolean operation, means we had a big, or we have this box here, and on this box we actually created a hole through it. So we subtracted this cylinder and created a hole. And then we eventually added this side of it, which is here, to form finally this. So you see the three forms shows the boolean. This was added, this was subtracted to generate this. So this is a typical constructed solid geometry tree. Now, what you notice in constructed solid geometry 2 is that they are not unique. That is, if I want to create this, I can create this by doing a union of these and that, and I will form this. Or I can do a subtraction of these from that. And then of course I will also generate this thing. And so it is not unique. There are several ways by which I can achieve this. So we say that it is not unique. Now, other things that you can find on constructed solid geometry representation is that they actually gives you unevaluated surfaces. So the faces, edges are not defined in explicit because there is no unique way of creating it. Their surfaces are unevaluated. Now, the other thing also to know is that the CSG models are always valid, since they are built from a valid base, which is a solid element. And they are also complete and they are unambiguous. These are points that we have to know from CSG. The other things that you need to know from constructed solid geometry is this. That is the advantages. They are very powerful high-level command in modeling CSG. You can use it to easily construct a solid model with minimum step. Now, constructed solid geometry technique also gives you a very concise database, straightforward database with less storage. Now you can actually retain the complete history of the model, and you can also alter it at any point if you so wish. It can also be converted to the corresponding boundary representation, which is the next one that we're going to look at in terms of the technique. Now CSG also has some disadvantages, because in CSG, it's only Boolean operations that are allowed. With Boolean operations, what you can do is really restricted, the shapes that you can generate. So when you have unusual shapes, it's not very possible to construct using the CSG technique. And sometimes you require a great deal of computation to derive the information of the boundary, faces, and also the edges, which is actually important for interactive display. Now the solution is to these disadvantages is that CSG representation tends to accompany the corresponding boundary representation, which is a hybrid representation. So you don't use only CSG, but it's a mix of CSG and then BREP, boundary representation, which we are going to look at very shortly. Now, the other thing too is you have to maintain the consistency between the two representations. That is, when you have boundary representation and CSG, you have to maintain how you consistently use them. Right. Now, when it comes to boundary representation, that is, we've dealt with this constructed solid geometry. So we're coming to the second most commonly used technique, which is boundary representation. In boundary representation, we say that for boundary representation for a solid, the topology, very important terminology, topology as well as the geometry of the solid, okay, is stored. So the representation will keep storage of the topology, the profile of the surface, and as well as the geometry of the solid. Now, the geometry models position, size, and orientation, whilst the topology will model adjacency and then connectivity. We will look at this very shortly. Now, one of the shortcomings of constructive solid geometry is that though you have constructive solid geometry models, the model, it does not display the topology of the surface, the orientation of the surface. So, when we talk about topology, we are looking at vertices, edges, and faces along with pointers, storing the connectivity information, because you need to know which vertex is connected to which vertex, which edge is connected to which edge to form a face. And this is what they call the topology information. So, for example, an edge joins two vertices, and you need to know those two vertices. A face is surrounded by one or more closed loop of edges, which has to be fully described. So the topological information is normally a binary data, which is a vertex. B is either on the edge or not on the edge. So it's a binary data which is 0 and 1. So if you're describing a vertex, the vertex 1 on the edge or 0 not on the edge. So 1 on edge 1, maybe 0 on edge 5. It means that this is 1, 0. It stores it as if that vertex is on this edge, but it's not on the other edge. Now when it comes to a face, the face is either adjacent to one other face or it's not adjacent. So it's face 1 meaning it's adjacent, 0 means it's not adjacent to this face. So this topology information allow you to answer some basic queries, such as if you want to find all the edges adjacent to a particular edge, or list all the faces surrounding a particular face, this information will just be displayed. Now this is what is missing from CSG representation. So when you take a typical boundary representation data structure, this is what we see. So if we take this shape represented by various vertices, edges, and faces, this is a solid, as you can see from view. Now from this solid we can break it down to the faces that form the solid, which we labeled it as phase 1, 2, 3, 4, 5. Okay, now these faces have edges forming closed loop around them. So if you take phase 1, you can describe the edges that form the loop around it. And then you take phase 2, you describe the edges that forms a loop around it. Now you notice that these edges also have vertices. Now each edge is connected, it's connecting two vertices. So you will see the connectivity information for each vertex. So all this combines to actually give you the topology. So this structure, normally called the combinatorial structure or called the topology. And then the metric information, which is a geometry information, is the x, y, z point coordinate. So when you take a typical point coordinate, which is this, is called the metric information or geometry information. But this structure, which is the data structure here, the topology information or combinatorial structure, is what makes a B-rep very complete in its description of the solid. It stores these points, very important, but as well as the topology, which is very important to completely describe the object. So we say that topology however, does not also store any information on position, size, and orientation of the vertices. Okay, then this numerical data is normally stored in the geometry. So the geometry of a solid will be points, curves, surfaces, along which this data is describing the position, size, and orientation of each point. For each curve or surface, the data for generating this parametric equations and everything will be stored in the geometry. But geometry also is not concerned with adjacency or connectivity. This is what you find in the topology information. So both this topology and geometry structures, they are complementary in the BREP, in the boundary rep. So topology and geometry are tied together by pointers. That is vertex points to points, and then edge to curves, then faces to surfaces. So this is how the topology and the geometry tie together. And this data structure gives you the geometry, the topology, and then the pointers from the topology to the geometry. Now, when you have this type of structure, we call it a boundary file representation, which is shortened as BREP. So we've seen how BREP structure is. Right. Now, if you take a boundary representation, for you to see whether or not this boundary representation is valid, we're saying that the system must validate the topology of the created solid. So, because it has to validate the topology, BREP has to fulfill certain conditions that disallow self-intersecting and open objects. Because you cannot have a solid with edges or features which are self-intersecting and then also open. So these conditions have to be fulfilled for you to have a valid topology information for your BREP. That is one. Each edge should adjoin exactly two faces and have a vertex at each point. You can find these things on every solid. For every solid, if you describe an edge will join exactly two faces and have a vertex at each point, at each end. Now, these vertices are geometrically described by a point coordinate or point coordinates. So each vertex each feature you call a vertex should be described by a coordinate point, x, y, z, in a three-dimensional space. Now, at least to have a vertex, you should have three edges meeting to form a vertex. Now, faces are described by surface equations. So every face can be described by an equation that will how to generate the surface. Now, the set of faces that you have on any solid will form a complete scheme of the solid around it with no missing parts. Okay, so we say that each face is bounded by an ordered set of edges. So if you take any typical face of an object, you will see edges forming around it to create the face. And they form what we call a loop, which is closed loop. Now the faces too must only intersect at common edges. The faces must only intersect at common edges or vertices. Now the boundaries of the faces also do not intersect themselves. So these are conditions for you to fulfill, to allow, or let's say to disallow self-intersection and open objects. That is, for you to create a valid boundary file, these conditions must be fulfilled. So, when it comes to boundary representation, this is what will make it valid in this representation. Now, when it comes to boundary representation too, there are issues with ambiguity and uniqueness. Now, for valid boundary representations, they are obviously unambiguous. If you are able to fulfill all these conditions, you will create a representation which is not ambiguous. However, the uniqueness is a little questionable. It's not fully unique, just like what you have in constructive solid geometry. Now, there are little differences that exist in the division of surfaces into faces and then having curves into edges. There is a little or potential differences that you may find. Okay. So, we come to the advantages, boundary representation advantages. Now, one is able to construct unusual shapes that will not be possible for CSG technique. That is, you can use it to do aircraft fuselage, swing shapes, and all that. Now, it requires less computational time to reconstruct, but if you compare it with the constructive solid geometry, then that is what we mean by less computational time. Now, the boundary representation also has some disadvantages. More storage space compared with CSG in a way. Now, it is more prone to validity failure than having CSG, because CSG is coming from valid solids. BREP, because you are creating it, sometimes there is that possibility of having an open object or which may not be a solid. Now, the model display is also limited to planar faces and linear edges. Now, when you have very complex curves and surfaces, what you normally see on the screen is only an approximation. So we say that the complex curve and surfaces can only be approximated. Okay. So now, we're looking at the final part of this unit, which is going to help us understand how to determine whether or not when you have a representation, you can say that it's a valid solid in the view. So we're going to look at this from an equation that has been developed by a French mathematician, Euler-Poincare. Now, Euler-Poincare equation is given as follows. That is V minus E plus F minus into L minus F minus 2 into S minus G should be equal to 0. Now, this is what Euler has expressed. Now, with this, Euler is saying that V is for vertices. V is for vertices, and then we have E for edges, plus F for faces, minus L minus F. Now, L is the loops, the number of loops, and then we have minus 2 into S is the shell, the number of shells, which we will talk about, then minus G, the G is called genus. Now, for vertices, I believe that we are familiar with vertices. Edges, we are. Faces. Now, when we talk about genus G, what we are talking about in the solid is the number of penetrated holes. Very important. If the hole penetrates, it's a see-through hole, then it's called a genus. Now the shell is the skin around the object. So every object has one shell around it. Now, unless there is an internal void in the object, the shell is always equal to 1. But if there is an internal void, which can only be seen from a cutout or from a section, then the number of shells will be the outer skin, which is 1, plus any internal void forming an inner skin to add to the shell. And L, of course, is the number of all outer and inner loops. So the loop, actually, when we talk about loops, then we are looking at, for a face, it is bounded by a loop. So if I take this face of this cube, I can say that this is the loop 1, 2, 3, and then 4. Okay, so I could basically describe all the edges here as the loop. So it's bounded, this face is bounded by 4 loops. This side is also 4 loops, and so I can count the number of loops. So we are going to look at the validity or otherwise of some solids by using Euler-Poincare equation to test whether or not the representation is a valid solid. So the first example that we're going to look at is a cube. Now we all know a cube is a valid solid, so we're just going to test the obvious by looking at the number of edges, the vertices, the loops, and then describe it. Now if you take a cube, it has 8 vertices, so V is 8. Now the number of edges, 12 for a cube. Now the cube has 6 faces. We can count them. Now for a cube with no holes, then the genus is going to be 0 because there is no holes. Now if the cube, which is a solid with no void, then the shell, which is the outer skin, shell which is S, is going to be 1. Now for the loops, when we look at the loops, we can actually look at this. This is one loop forming the face. This is another loop going around 1, 2, 3, 4 from this face, and we can count as many as 6 loops. Okay, so we have 8 edges, 12 edges, 8 vertices, 12 edges, and then we have 6 loops. 1 shell, no genus. Okay, so when we apply the Euler-Poincare equation, basically, if you have this equation, as I've already explained, we have vertices, edges, and then the loops, so we've counted them. Now, if we do these maths, we can basically see V minus E plus F, and then into L minus F and all that, we get the answer to be 0. Now, once we get the answer to be 0, we fulfill what Euler-Poincare is saying. It is very straightforward because a cube is a valid solid. Okay, so a cube is a valid solid, and therefore the equation has proven to be so, that it's a valid solid. Now we can move on to look at the next example to test whether or not this also is a valid solid. Now let's say we have a cube that we have cut out, a cube within a cube. So you have a cube, but there's a cutout of a cube inside there. So this has lost one face. So it's actually a cutout, but it's not penetrating. It gets to a certain depth this way. Now, if we want to count the number of vertices in this, we basically have two cubes, a cube and then a cube within a cube. So we have 8 edges for this bigger cube and then another 8 edges which you can count inside this, and then get, of course, you can count these 8 edges inside, then these 8 edges outside to get to 16. 8 vertices to get to 16. Now we can count these edges outside here, which are of course 12, and we can also count the edges inside here as also 12 to give you 24. But when it comes to the number of faces, we can count 6 faces for this bigger block, but when we come to the inner cube, you notice that it has lost one face, so it is 6 plus 5, we have 11. Now this hole is not a genius because this cutout is not penetrating, so there are no holes. G is 0. The shell, of course, is the outer skin, and that is 1. So this is not displaying any internal void. This is exposed, so the shell is 1. The number of loops, we could define 6 loops around the bigger cube here, and then the cutout too, we can define the loops. Even though this face has lost one face, but the loop is still there, then we can also describe the other 5 loops. So we have 12 loops. So applying the Euler-Poincare equation again, we can get 0, meaning that this is also a valid solid. That is okay. Now let's look at this representation too. We have a cube that has been cut out in this cube, but this time it is penetrating. We have a hole, a see-through. Okay. Now in this see-through, you notice that the number of vertices still remain 8 here and then 8 inside. That gives you 16. The number of edges also has 12 outside and then 12 inside, giving you 24. But the inner cube has lost 2 faces, meaning that the number of faces are now reduced. We have 6 here, and then we have the remaining 4, making it 10. Now the genius, which is the penetrating hole, is 1, because there's a hole, a see-through. Now the shell is still 1 because the outer skin, there is no internal void. The internal void that we describe is a void which can only be seen when you section. But this one is a hole, a see-through, which you can see. So the shell is still 1. And the number of loops remain 12 because you have 6 and then 6 in the inner cube. When we do the Euler-Poincare equation construction, we still get 0, meaning this is a valid solid, which is true. Now, we move on to look at this representation, example 4. Now, this, we need to pay attention to this a bit because this is a solid which has a penetrating hole here. This is penetrating because when you cut off, now this view is showing a section through this. This is the section plane. So when you cut this away, then you will see this as a section. So this is a see-through. And then once we cut through, we notice that there is an internal cubic chamber. That is what is being described from the problem. Internal cubic chamber shown by the right cut away figure, this figure on the right. Now, when we use the Euler-Poincare equation to determine the validity, we will notice that this figure, the number of vertices, you can basically look at this as having three cubes. The internal one, this cube here, and then the main block, which is a cube. So the number of vertices will be 8 by 8 by 8, and that is 24. Now, the number of vertices, 24, number of edges, each of the cube will contribute 12 edges, so 12 by 3 will have 36 edges. Now, the number of faces, you notice that this cube that is cut away here, the see-through one, has lost 2 faces. Hitherto, each of them would have contributed 6 faces, which is the internal cubic chamber, the block itself, and then this cube. And so that would have been 6 by 3, 18, but minus the 2 that has been lost by this. So you have 16. Now the genius is 1 because there's one penetrating hole here. Then the interesting thing here is that the shell is not 1. Now the shell is 2. 1 is the outer skin, and then the second one is revealed from the cutout, which is displaying an internal cubic chamber, which is an internal void which can only be displayed through a section. So that gives us a number of shells as 2. Okay, so when it comes to the number of loops, all the loops remain in place. So we have 3 cubes, each of them having 6 loops, so 18 loops. When we do the Euler equation, we will still get 0, meaning that this representation we see here is a valid solid, which is also truly obvious. Now, so far, the equation is holding good. Now, let's look at this and then final. Now, for all this that we have looked at, a visual inspection of the solids in that example can easily tell us that the objects are valid. So the Euler equation by itself can only be used to conclusively determine that an object is not a solid. When the value is not equal to 0, that is, if the value is not equal to 0, then we can clearly see that the object is not a solid. However, there are some representation that you can have the value of the Euler-Poincare equation being 0, but does not guarantee the representation is a valid representation. Now, this example is going to demonstrate that. Now, let's assume that we have a cube here, and then we have this flap, which has this bounded to this edge here. Now, if we have this representation, now let's do accounting the number of vertices. The cube actually has 8 vertices, plus these 2, we will have 10 vertices. If we so describe this as a vertex. Now the number of edges, the cube has 12, then we can add 1, 2, that is 1, we can add 1, 2, and then 3, and then we have 15 edges. The number of faces, we describe the cube having 6 faces, and then we add this side as a 7th face, then we have that. Then the shell obviously is the skin around it is 1. There's no penetrating hole, so the genius is 0. Now when we do this construction, we will get 0. But as we can see, this is not a valid representation. The reason is that if you take what B-Rep was able to show us, now we said that a vertex can only be formed when you have at least 3 edges. So this cannot be a proper vertex. This cannot be a proper vertex. This cannot also be a proper face because this face must not interpenetrate. When we look through here, we should not have a see-through. If we don't see through this two, then it means that this side has to be a double edge. Means it's a solid. So with this strip around here, this fails to be a face too. So it means that the Euler equation is not sufficient to just tell you whether or not a representation is a valid solid. The only time it holds true is that if it is not equal to 0, then you can conclusively say it is not a valid solid. But if it is 0, you need additional information to tell you that this representation is not valid. Now, these are the additional information conditions that you require to be able to show you whether or not this representation is not valid. Now, one is that each edge must contain 2 vertices. Now, these vertices must be shared by 2 faces. Now, at least 3 edges must form a vertex, must meet. Otherwise, if it is not at least, so it's 3 or more. Now, faces must also not interpenetrate. Very critical. Right, so these 4 conditions plus the equation could help you determine whether or not a representation is a valid one. Okay, now these are some self-assessment guides that you can look at in the list. The advantages of wireframe models, the major differences between a surface model and a solid model. You can also state the Euler-Poincare equation and explain the terms, the limitations with regard to determining the validity of the solid. You can also explain that these are self-assessment questions. So this is the second assignment, which is if you have this wireframe model shown here, if the cube is of unit length, the origin at the center of the cube, to construct its vertex and an edge table. This part, you may not need to do this because it is actually in the notes. We use it in an illustration. But the second question is what I want you to look at, which is the second and the third one, which I'm going to show you shortly. Determine the validity of the object shown. This diamond shape, check the number of edges, faces, and use the Euler-Poincare equation to actually, in addition to those 4 conditions, to determine whether or not this is valid. As well as this is a cylindrical shape with a square cutout inside. So, and a task you have is to find how many edges a cylinder has. Okay, you have to be able to determine the number of edges that a cylinder has, whether this is an edge and whether this is a face or not. Whether these sides that you see here is describe an edge or not on a cylinder. So that is your task, to determine the number of edges and faces that a cylinder has. This is a square cutout, so that is an obvious one. Okay, so these are the 3 questions, and I want to thank you for listening and learning this unit. You can review the videos again, and for any queries or concerns, you may contact the numbers listed below. Thank you once again, and have a good evening.